Hello everyone, welcome back to the channel. So in the last session we have discussed about atomic and ionic radii of F block elements, how that atomic and ionic radii varies in case of lanthanides, even we consider actinides. Well, in this session we are going to discuss the one more concept of a chapter, that is oxidation state of lanthanides. Okay, oxidation state of a lanthanides. Well, so if you consider oxidation states, we know that it depends on what? It depends on the number of electrons present in the valence shell. Andre oxidation state ಯಾವ್ದ್ರ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿರುತ್ತೆ? It depends on the number of electrons present in the valence shell. Yes, if you consider elements of the lanthanide series and we consider the outer electronic configuration. So yes, lanthanum La, if you consider outer electronic configuration 4f0 5d1 6s2, it is the electronic configuration for lanthanum. Next cerium 4f1 5d1 6s2, praseodymium 4f3 5d0 6s2, neodymium Nd 4f4 5d0 6s2, promethium, okay, 4f5 5d0 6s2, then samarium Sm 4f6 5d0 6s2, then europium Eu 4f7, okay, 5d0 6s2, then coming to the gadolinium 4f7 5d1 6s2. Say now if you consider the outer electronic configuration of these elements, say lanthanum, if I consider the first element lanthanum 4f0 5d1 6s2, how many electrons are present in the outer orbitals? 3 electrons. In 1 electron present in D subshell and 2 electrons present in S subshell. As like if you consider the outer electrons present in the outer electrons in the sense the electrons present in the outermost orbitals, they are going to take part in a reaction. Hence we say the oxidation state of the element depends on what? Depends on the number of electrons present in the outermost orbitals. Okay, yes. Now if you consider lanthanum 4f0 5d1 6s2, and even if you consider gadolinium 4f7 5d1 6s2, say 4f0, f0 means is a stable configuration, means stable, and 4f7 for f7 means it is half filled, which is also most stable form, okay, stable configuration, and the fourth last one f14 completely filled configuration is also most stable one. Therefore if I consider lanthanum and gadolinium, okay, what is the oxidation state they may exhibit? Say lanthanum, it can lose all these 3 electrons, therefore it shows +3 oxidation state. And if I consider gadolinium, it also loses 3 electrons, so shows +3 oxidation state. So overall for lanthanides, what is the most common oxidation state is the +3. Okay, +3 is the most common oxidation state. So for lanthanum, if 3 electrons were lost, what is the configuration? It becomes 4f0 5d0 6s0, means here the electrons present in 5d and 6s2, these electrons are lost, so that is going to acquire a +3 oxidation state. Okay, so 4f0 5d0 6s0. Then coming to the cerium, if it shows +3 oxidation state, say 1 electron from 5d and 2 electron from 6s will be lost, so 4f1 5d0 6s0. Then similarly if you consider promethium 4f2 5d0 6s0, neodymium 4f3 5d0 6s0, then promethium 4f0 5d0 6s0, samarium 4f5 5d0 6s0. So in case of europium, please remember, so in case of europium, say it already has a stable configuration, right? 4f7 5d0 6s2. So there is only 2 electron in the S subshell, but there is no electron in D, is already going to have a stable configuration. Means if at all it shows +3 oxidation state, means is it stable or unstable? It is unstable. So for europium, +3 oxidation state is unstable. Why we are saying it is unstable? Means since is going to have already a stable configuration. Then which is stable? It may show +2 oxidation state. If it loses these 2 electron, okay, if it loses the 2 electron, will be going to get a half-filled configuration. So going to get a stable, more stable configuration. Say yes, if at all it loses 3 electron, means what is the remaining configuration? 4f6 5d0 6s0. Well, then for gadolinium, yes, it readily loses 3 electrons, so that is going to get a half a filled configuration, 4f7 5d0 6s0. Well, now lanthanum and gadolinium, they readily show +3 oxidation state. Reason, by losing 3 electron, lanthanum acquires F0 configuration, which is stable, and in case of gadolinium, by losing 3 electron, gadolinium acquires a half-filled, stable half-filled configuration. Okay, yes. Now coming to what are the elements I specified already? Europium and one more, neodymium. Okay, europium and neodymium. Say they even show +2 oxidation state. Okay, +2 oxidation state, which means if it loses 2 electron, what is the configuration? So in case of europium, it is 4f7 5d0 6s0, and if you consider neodymium, even it also shows the +4 oxidation state. Cerium also shows a +4 oxidation state. Say in +4 oxidation state, if cerium loses 4 electron, what is the configuration? 4f0 5d0 6s0. So again 4f0 stable, and neodymium also shows +4 oxidation state. Okay, yes. Now if you analyze that table, what we can see here, the most common oxidation state. What is the most common oxidation state for lanthanides? It is the +3. Okay, +3 is the most common oxidation state of lanthanides. Okay, is the one thing. Further, the +2 and +4 oxidation states, the +2 and +4 oxidation states are also shown, which can be explained on the basis of thermodynamic stabilities. Okay, so yes, there are some elements which shows even +2 and +4 oxidation states. It can be explained on the basis of thermodynamic stabilities. Well, then the next thing to be remembered is neodymium. Okay, neodymium, samarium, europium, thulium and lutetium. Nd, Sm, Eu, Tm and Lu. Neodymium, samarium, europium, thulium and lutetium can act as a good reducing agents. We know the meaning of reducing agent. Reducing agents reduces other chemical species by itself undergoing oxidation. Okay, by itself undergoing oxidation. Then other set of elements, cerium, praseodymium, neodymium, terbium and dysprosium. I repeat, cerium, praseodymium, neodymium, okay, terbium and dysprosium. They act as a good oxidizing agent. So oxidizing agent oxidizes other chemical species by itself undergoing what? By itself undergoing reduction. Is other set of elements. So here neodymium, if I consider neodymium, it acts as a both oxidizing as well as reducing agent. As we said, it shows +2, +3 and +4 oxidation state. Okay, yes. So what is remembered here? As we know, reducing agents donate electrons readily. Okay, reducing agent reduces other chemical species by itself undergoing oxidation, means they readily loses electron, or I can say donate electron. Then what about oxidizing agent? Oxidizing agent oxidizes other chemical species, okay, by undergoing reduction, that is by accepting electrons. So oxidizing agents accept electron readily. Okay, yes. Now the oxidation state, what it is actually? It is the net numerical charge. So what is the oxidation state means? It is the net numerical charge present on an atom of an element in its combined state. Okay, say the net numerical charge present on an atom of an element in its combined state is called oxidation state, or it is also called oxidation number. Okay, yes. Now if you consider all F block elements, okay, that is lanthanides as well as actinides. All F block elements are generally they are metals. Metals means they have a tendency of losing one or more electrons. So if you consider the F block elements, their nature is they are metallic in nature and they show tendency of losing one or more electrons. Therefore, what we can say, they show positive oxidation state. Okay, yes. So if I consider general electronic configuration, 4f 1 to 14, 5d 0 to 1, 6s2, right? So all lanthanides shows a common oxidation state. What we said, +3 oxidation state. How they are going to get +3 oxidation state? By losing one electron. Okay, how they are going to acquire +3 oxidation state means by losing one electron from 5d and 2 electrons from 6s orbital. Okay, yes, we know generally the common oxidation state of lanthanides is +3. Okay, how they are going to show +3 oxidation state means by losing 3 electrons, 1 electron from 5d orbitals and 2 electrons from 6s orbitals. So that overall by losing 3 electrons they show a +3 oxidation state, which is the common oxidation state of a lanthanides. Okay. Now in addition to +3, okay, other than +3, yes, they also show +2 and +4 oxidation state. Okay, now common is +3 oxidation state. Yes, along with +3 they even show +2 and +4 oxidation states. So +2 and +3 oxidation states. Okay, +2 and +3 oxidation states are shown by europium and ytterbium. So europium +2 oxidation state, 4f7. If it loses 2 electron as I already specified, so is going to get what? 4f half filled. 4f exactly half filled configuration, which means if it is going to have a half filled configuration, it will be more stable. Therefore we say it readily loses 2 electron to show a +2 oxidation state. Okay, so if there is a europium, okay, europium 3 plus, say if there is europium 3 plus, means by accepting one electron it readily get converted into europium 2 plus. Means what happened? Europium 3 plus is undergoing what? Is undergoing europium 3 plus is undergoing what? What is this reaction? Addition of electron is nothing but reduction. Okay, yes or no? Is undergoing reduction. In the sense europium 3 plus is undergoing reduction, therefore europium 3 plus act as a what? It act as a oxidizing agent. Europium 3 plus act as an oxidizing agent. It oxidizes other chemical species by itself undergoing reduction and get converted into europium 2 plus is going to have 4f7, a half filled configuration, so it is more stable. You got it? Yes. Then if you consider ytterbium shows +2 oxidation state. Okay, so even same here also. So if there are ytterbium 3 plus, ytterbium 3 plus, so by accepting electron is immediately converted into ytterbium 2 plus. Why it has a tendency means ytterbium 3 plus by accepting electron it reduces to +2 oxidation state, and in +2 oxidation state is going to have exactly completely filled configuration, therefore which will be more stable. Therefore europium 3 plus and ytterbium 3 plus they act as a good oxidizing agent. Please remember europium 3 plus and ytterbium 3 plus they act as a good oxidizing agent. Okay, yes. Then coming to the +3 and +4 oxidation states, these are shown by, say for example, cerium. Cerium atomic number 58, electronic configuration 4f2, 5d0, 6s2. So cerium 4 plus means what? Cerium 4 plus means all 4 electrons were lost here. 2 electrons from 4f and 2 electrons from 6s. All 4 electrons are lost. So cerium 4 plus by losing 4 electron is going to get what? A 4f0. 4f0 means it's a empty orbital, so again it is more stable. So cerium is, it readily shows +4 oxidation states. Okay, then terbium, atomic number 65. So electronic configuration 4f9 5d0 6s2. Terbium, if it loses 4 electron, okay, after losing 4 electron is going to get a half filled configuration 4f7 5d0 6s0. Therefore it also readily loses terbium, readily loses 4 electron to form terbium 4 plus. Okay, yes. Then coming to the MCQs, the first one, what is the electronic configuration of lanthanum in +3 oxidation state? Okay, say we know for lanthanum 4f0 5d1 6s2 is the electronic configuration. So for lanthanum, outer configuration is 4f0 5d1 6s2. They are saying lanthanum 3 plus. 3 plus means those 3 electrons were lost. So 4f0 5d0 6s0 is the configuration. So we look for option first. The first option 4f0 5d0 6s0, 4f0 5d1 6s2, 4f1 5d1 6s1, 4f0 5d3 6s0. So what is the answer? Option A is correct. 4f0 5d0 6s0. Okay, yes. Then the second one, what is the most common oxidation state of a lanthanides? So yes, we already mentioned it. Most common oxidation state is the +3, right? So we look for an option first, +2, +3, +4 and +5. So what is the answer? +3 is the most common oxidation state. So option B is correct. Okay, well, next one, A block elements are good. A oxidizing agent, B reducing agent, reducing as well as oxidizing agent, and none of the above. Yes, what about A block elements? Yes, they act as good oxidizing as well as reducing agents. So option C is correct. Well, next one, +2 oxidation state is shown by which of the following element? +2 oxidation state is shown by which of the following elements? First one, europium, B, okay, terbium, both A and B, none of the above. Yes, what is the answer? Answer A and B, that is both A and B. Europium also shows +2 oxidation state, ytterbium also shows +2 oxidation state. Okay, so option C is correct. +4 oxidation state is shown by which of the following element? Cerium, okay, terbium, both A and B, none of the above. Yes, answer C, both A and B. Cerium also shows +4 oxidation state, so that is going to get a 4f0 configuration. Terbium, by losing 4 electrons, it also shows a 4f7, that is exactly half filled configuration, right? Well, so with this I am going to conclude about this session. Again in the next session we go for other concept. Thank you. Be safe.